Thank you for the introduction. Like it was mentioned, my name is Ian. That's a topic I really like talking about, and like we said, I've been doing Python for a while now and really like it. I really like giving this talk, and I hope everyone will have a fun listening to it and enjoy it. A little bit about motivation. So I think our industry and engineering industries in general can benefit from learning from past mistakes and the past incidents that happened. And this is my way to kind of promote that and help us learn, not necessarily from our organization, but also from different organizations. So we will start with what is a bug. So the easiest thing, let's go to Wikipedia. And Wikipedia says a software bug is an error flow failure or fault in a computer program or system that causes it to produce an incorrect or unexpected result or to behave in unintended ways. There is a common or so common misconception that the word bugs or reference to bugs in computer software comes from when we had big, huge mainframes. Bugs would go into those huge mainframes and cause errors. But actually, if you look historically, it was actually people started referring to inventions and something that is buggy in mechanical machines way before the invention of computers. You can actually, the first recorded incident is a letter that is signed by Thomas Edison, where he actually referred to one of his inventions as being buggy. But what I find really cool is this note that comes from a log of a group of engineers working on the Mark II computer at Harvard University in 1947. They actually recorded this moth that entered into the computer. They found it. It short-circuited one of the relays. And you can find here, you can see that it says first actual case of a bug being found. If you're really interested, I haven't really seen it myself, but I do know this is stored in the Smithsonian, and you might be able to see that in person. So today we'll talk about famous bugs. We'll review bugs from several industries, and one of my favorite is to talk about the space industry. So we'll start there. The Mars Climate Orbiter, that was a mission that was launched by NASA in December of 1998. The purpose was to collect information about past Mars climate, about possible water distribution, temperature profile, and the past climate change. In about 9 months after launch, the orbiter has reached close to Mars, and it was supposed to perform a series of maneuvers, as you can see here, in order to go into stable Mars orbit. Unfortunately, what was discovered later is that the thrusters that were built by Lockheed Martin were using the using the metric unit, unit measurement, versus the actual system controlling those thrusters was built by NASA themselves, and that was using the empirical units. That caused the thrusters to operate about 4.5 times more, basically much stronger than they were supposed to. The orbiters assumed that it wasn't able to achieve a correct orbit around Mars, and it was probably burned as in the reentry into Mars itself, and we have lost contact with it. The result was that quite substantial, obviously, financial damage, losing over $320 million, 4 years of research and development, and a substantial delay in the research of Mars that impacted us with the research that is still ongoing and possible sending people to Mars. Specifically, why do we want to talk about this bug, what I find interesting? What I find especially interesting in this case is that Lockheed Martin, based on the commission that was established by NASA, received the spec how they should have built those thrusters, and they did not follow the spec. They got the spec indicated the correct measure of units. But NASA did not put the blame on Lockheed Martin. They actually acknowledged that any big software development project like this would have software problems. And they actually, NASA put the blame on their own internal testing procedures that they thought should have caught this kind of an error much earlier in the process. And it should never have been allowed to reach such a catastrophic result. The other part of it, NASA also discovered that the team that was in charge of the maneuvering and the guidance in the months leading to the incidents actually did complain about, they did have concerns about the thrusters operating incorrectly. But the bug ticket that they have filed didn't get the correct priority. And that was another, basically, not just the miscommunication between the different software systems, but also a miscommunication between the different human teams. With that, the second bug I would like to talk about is another space bug. This one will go from NASA over to the European Space Agency in early or mid-1996, in June 1996. The European Space Agency was switching from their Ariane Mark IV to Ariane Mark V rocket. This was the first actual launch of the Ariane Mark V. It was supposed to be both the final test, but also it was carrying 4 satellites to be used operationally and to get better insights into how the interaction between Earth's magnetic field and the sun. About 37 seconds into the launch, what is called the inertial guidance system or the inertial reference system has malfunctioned, and due to sending incorrect values to the guidance computer, to the rocket computer, basically the rocket have self-destructed. What actually happened, so this is the only the slide that I have code on, and it is not Python, this is Ada code. But what you can see here is that actually the inertial reference system, that was a very reliable system that was developed for the Mark IV rocket. Because it was very reliable and it was easy to just reuse it, it was reused again in the Mark V. But the Mark V did have substantial differences compared to the Mark IV. What happened was that shortly before the actual launch, the countdown was halted, but then it was very quickly resumed. That was the procedure for the Mark V. That wouldn't have happened in the Mark IV. This was actually an auditing or a testing subroutine that wasn't supposed to be in operation in a live launch. But due to the fast resume of the countdown, it was actually active those 40 seconds into the launch. There are 7 variables that are used here, and they're being converted, and there was a loss of precision. And the one crucial one that we're seeing here, that one was actually not protected against an overflow. That caused sending the wrong value, and once that was detected, there was a switch to the backup system, but the backup system basically malfunctioned in the exact same way. So that's how we got the tragic result of that missile exploding. The total cost was $370 million that were lost between both the rocket and losing those satellite. The bigger impact was actually that the European Space Agency had a very good track record with their Mark 3 and Mark 4 Ariane rockets. And by having that very public failure, that actually set back their brand and the confidence in them reliably sending rockets. One actually positive impact was from that due to how this incident was researched and understanding the error that was put there in the code, that actually led to development of quite a few static analysis tools that we are still using up to today. And something interesting that I found in the last few weeks when I was re-preparing this slide is actually that the Ariane Mark 5 has completed its life about a year ago. At mid-2023, that was the final 117th launch, and they are now in the process of switching to the Ariane Mark 6. So why this bug specifically? So there are two main points that I found interesting. One is that a lot of times we take a software package that was reliably used in one project or in one system. And because we used it quite well, it worked for us, we reuse again that software package or code again in a different system. That was basically what happened here. But a lot of times we don't think that in a new project it actually has different requirements, have a different testing or profile that we need to do. This is exactly what happened here. There wasn't enough of understanding that this was a totally different profile of a rocket, and it should have been re-examined much more closely if that system was applicable for it. The other part is that's very common, especially with the military or space systems, is that there is a backup system that is supposed to kick in and be effective when there is an error. But in a case like this, where there was a fundamental problem with the code, the backup system was basically very ineffective because it was the exact same error that happened with the backup system. And now, in a quick switch to a totally different industry, AT&T placing long-distance calls. So this is a picture of Alexander Graham Bell placing the first long-distance call between New York and Chicago. And in January 1990, AT&T that had a very reliable backend system to place long-distance calls, they suffered a very big outage lasting 9 hours with most people on their network not being able to place long-distance calls. What actually happened was that the backbone and the main infrastructure for their reliable system was a network of over 100 of these switches. They were very reliable, and AT&T has placed a lot of effort into in the software, in the hardware. About a month before the incident happened, AT&T deployed a small software update with the intention to be able to have these switches in case that they had a malfunction or they were overloaded, to be able to restart faster. Unfortunately, that software update, although it was supposed to make the system better, it started with the one switch being overwhelmed and causing a self-restart, which was pretty common. However, when it came back up, it alerted another switch that it was back in operation, but it sent very quickly. It sent another message saying, again, confirming that it is in operation. Because the system now operated very quickly, the other switch that received those messages actually saw that that didn't make sense and diagnosed itself as malfunctioning and restarted itself, basically. That caused pretty much a cascading effect of switches across the network just continuously restarting themselves. And it took AT&T's engineers about 9 hours until they were able to stabilize the system and effectively bring it back up. The results is that obviously there was a substantial PR damage to AT&T. They suffered about $60 million in unplaced lost revenue from unplaced calls, about 75 million phone calls that weren't placed, and of course, as I mentioned, the brand name reputation because to the reliable system that they have built. So why this bug specifically? Again, in this case, AT&T has spent a lot of effort into making a very reliable system. They called it, basically it was that each component in the system was able to diagnose if other components that are connected to it are misbehaving, and by that kind of having a self-healing system. But in this case, they wanted to make a small update to the system to make it a little bit faster, a little bit more reliable, but they failed to understand how it might affect the entire system that is in operation and not really doing the full end-to-end testing with an entire system, and that caused the cascading effect. And now a much more tragic incident with a Patriot system. So you may or may not be familiar with the Patriot system, which is a system of ground-to-air missiles intended to be deployed in either military bases or some sensitive installations and protect against other ground-to-ground missiles. Basically, you have a battery like this, which has several missiles that are used for interception. One of these battery systems was deployed during the 1990s, and in 1991 in Saudi Arabia, an American Air Force base in Daharam, an Iraqi Scud missile was fired towards this base. The Patriot system that was protecting the base has detected the incoming missile and tried to intercept it. However, it failed to intercept it, and the missile did hit the base. What actually happened is a little bit understanding of the physics and the internals that how this system works. Is if you go and you see this first slide, or the first representation, is basically the system detects an incoming missile, it calculates a trajectory, and then there is this what's called a cone of certainty where the system would know where the missile would be. Now this is how the system should operate. This is how it would operate under normal circumstances. In this case, we see that it again detected the missile and calculated the trajectory, but this system has been operating, I think, for about 8 hours or so. And you see how now the missile is not exactly in the middle, but it's almost at the edge of where the system can project where it will be. In this case, the system has been operating, I think, for something like 20 hours or more. And what happened here is the system is completely unable to detect the incoming missile. The reason for that is that the system, in order to effectively detect and project the trajectory of the missile, it needs to have an internal clock that was activated, and unfortunately, due to precision errors, it also had some overflow that need to be corrected. Surprisingly, actually, is the fact that the software developers did understand they need to compensate for that overflow, and they created some code to account for that. However, very unfortunately, they applied that subroutine only in one place versus there were two places that they needed to do it. That caused basically a drift between the two system clocks. And that created a drift that would make it impossible to track the missile. Now, unfortunately, the results were that about 28 people, 28 personnel were killed on the base, and 110 were injured. Most of them were reserve duty personnel from Pennsylvania. And that definitely contributed. You might be aware of a debate about the precision of the Patriot missile system and its effectiveness. Specifically, why I wanted to talk about this bug is the reason that actually some of the places where the system was deployed, they actually reported to the project management of this operations about this problem. However, at first they were unable to reproduce that, and for a while they said that that is not a problem, and they kind of ignored it. Later on, they did acknowledge that that was a problem, and while developing a code fix for it, they sent an advisory to the different locations that they had the system deployed. Unfortunately, the advisory said that in order to mitigate the issue, the system needs to be restarted after operating for an extended period of time. For them, an extended period of time was somewhere above 8 hours, but in a case like this with the base in Tehran, which was on a constant alert during that time, they wanted to keep the system going as much as possible, and they didn't understand the full ramification. Their system was actually operating for over 100 hours. So basically no chance of correctly intercepting that missile, and basically that miscommunication on a few levels that caused this tragic effect. So since we're running quite a bit on time, I'll go briefly over this last bug, which was an incident happening in 1983, where the Russian system that was supposed to detect nuclear incoming missiles has detected in the evening of September 26, 1983, it detected the 5 incoming missiles from the continental US. What basically happened was that there was a constellation of events of a very consistent and wide cloud coverage across the continental US, combined with the sun alignment that basically overloaded the IR sensors in the system. The system created obviously what was false alarms, and it alerted the operators. Fortunately for us, the specific individual that was in charge of the system at the time, even though according to procedure, he was supposed to, if it was detection of more than one missile, he was supposed to directly forward it to his commanders that would initiate second strike capabilities. However, he decided that that doesn't make sense, that it would be only 5 missiles coming, that it would normally be hundreds of them, or at least dozens. And he decided to wait and basically see, and it was confirmed that he was correct. And basically, the idea for this bug is pretty much this, that first of all, when doing this kind of a critical system, you should be probably testing any edge case that you can possibly think of because of the consequences that might happen. And the second part is that I think even now, even with the ChatGPT and AI, as much as they're coming into fruition and the amazing capabilities that they have, that human intervention and supervision and the ability to say that it doesn't make sense, the incoming 5 missiles, that still has a lot of merit to it. With that, I think we're about out of time. As you can probably can tell, I really like the subject. I like to talk about it. If you're interested, please come and see me. I'll be here throughout the conference and would be very happy to talk about it. Thank you all very much and have a fun PyCascades.